Our 7th learning goal for Unit 1 is that you will be able to explain trends in atomic properties and the electronic structure and periodicity. So can you relate the electron configuration to and see those patterns, and can you then relate that to trends in the atomic properties? So let's review some of those trends. The first one is size, remembering that as you go down on the periodic table, the size increases because you're adding a new shell. That's relatively intuitive. We know that as the number gets bigger, the size gets bigger. But what's counterintuitive is what happens as you go across the periodic table. Remember we said that as you go across the periodic table, they're all in the same shell. So the relative distance is approximately the same, except for what's happening is as you go across, more protons are being added to the nucleus, which is more attractive to the electrons. And the electrons the shielding doesn't change. Like all the electrons underneath the valence electron, they're all the same number as you go across, right? The noble gas configuration, all the completed orbitals aren't changing. It's only what's on the outside that's changing. So as you go across the periodic table and the protons are getting greater in the nucleus, the attraction is getting greater and actually pulls everything in. And so the atomic size gets smaller by comparison as you go across the periodic table. So we call that a greater effective nuclear charge, pulling in those valence electrons and making this smaller. So effective nuclear charge means that the charge on the nucleus minus the electrons that are shielding the nucleus from the valence electrons, it's getting bigger because the protons the number is getting greater, but the shielding electrons are staying the same. So the effective nuclear charge that's reaching the outer layer is greater as you go across, and that shrinks everything down and makes the atomic size decrease, even though the atomic number is increasing. Even though the number of electrons is increasing, the size is decreasing as you go across. And that's a really important concept. It also is associated with the ionization energy. So the ionization energy, remember that's the energy to remove an electron from and that goes back to what we just talked about with photoelectron spectroscopy. The ionization energy is like the binding energy. How much energy does it cost you to remove an electron? And so this also, it decreases as you go down because the electrons that you're removing are the ones on the outside. And so they become easier to remove because they're further away from the nucleus. The distance is greater, and so they don't feel that attraction as much. But as you go across the periodic table, the ionization energy increases because the electrons they have that attraction to the nucleus. The size is smaller, the distance is smaller, the effective nuclear charge is greater, and so it takes more energy to remove an electron as you go across the periodic table. And the trends for electronegativity are exactly the same as ionization energy, and for the same reasons. So what was electronegativity? It was the attractiveness of the atom to electrons that are not part of that atom. So like in a bonding relationship, or even in any bonding, ionic bonding usually happens when there's a big difference in electronegativity. So something that is very electronegative is highly attractive to electrons that are not its own, or even a covalent bond, right? That even though the electrons are shared, the electronegativity means that they're more attracted to the one that is more electronegative. Even though the electrons are technically shared, they might be closer to the more electronegative atom because it's more attractive to electrons that aren't its own. Okay, so all of these things relate back to something called Coulomb's law, which is not really something that we talk about, in great detail in general chemistry your first year, but it is something that you will need to know and understand for AP chemistry, and you need to be able to comfortably say this relates to Coulomb's law. And things are going to relate to Coulomb's law when you're talking about charge attractions and the magnitude of the charge and the distance between the two charged particles. So actually Coulomb's law looks a lot like gravitational constant, or the gravitational law as well. So something interesting for you to think about how those two are related. But you can see that it's related to the charge and the product of those charges divided by the distance between them. And so if the distance is greater, that puts a bigger number in the denominator of this calculation. And when you have a big number in the denominator, that number, the overall number, is smaller, right? Like large numbers in the denominator are very small fractions. So as the distance goes up, the attraction goes down. And conversely, as the charge value goes up, the attraction goes up, because that's in the numerator of Coulomb's law. So being comfortable saying when you're talking about charge attractions and how they relate to Coulomb's law is mostly about the magnitude of the charge and the distance between the two particles. All right, so let's look at some examples. So the first question has to do with electronegativity between chlorine and fluorine. So go ahead and take a look at your periodic table, pause the video, and see if you can answer this question. Okay, so it says the electronegativity of chlorine is less than fluorine, and we just said that that has to do with two things. It could be if you're going across the periodic table or if you're going down. Now, in this case, fluorine to chlorine, chlorine is below fluorine on the periodic table, and so what we see is that it has an additional shell, right? And so what would that result in here? We've got the mass. We're not concerned with mass. Mass doesn't have anything to do with charge or distance. The chlorine nucleus contains more protons. That is true. But protons are more attractive, and so if it was just about the protons, then we would expect the chlorine electronegativity to be greater, but it's not. So this B is wrong as well. We've got when chlorine and fluorine form bonds with other atoms, the chlorine bonding electrons are more shielded than the fluorine bond. So remember, electronegativity has to do with the attractiveness of other electrons. So this makes sense that bonding would be involved. And the chlorine electrons are more shielded because they're further out. There's another shell, right? And so all those electrons on the inside of that shell are shielding the chlorine nucleus from the attractive forces of the electrons further out. C is actually the correct answer here. And then D, it says because chlorine is larger, the repulsion among electrons in the valence shell of chlorine are less. We're not concerned about repulsions in the valence shell. The only repulsions that we're concerned about are the shielding electrons, the ones that are between the nucleus and the attractive protons and the electrons on the outside. So all the ones on the outside pushing against each other, that's not what we're looking at here. So C is the correct answer. Okay, let's try the next example. Go ahead and pause the video and push play when you're ready to see how you did. All right, so in this one, we've got some information about calcium, and they're asking us what we would predict the information of potassium to be. So we need to find calcium and potassium on the periodic table. They're right next to each other. Potassium is to the left, calcium is to the right. So as we go from left to right, we know that the atomic radius should go down, right? And that the ionization energy should go up, because the electrons are closer to the nucleus, they're more attracted, which means that it's going to take more energy to remove them. So of these choices, we need something that has a smaller radius than 194. That means that we're limited to choice C and D. Both of those have a smaller atomic radius. We want the ionization energy to go up because it's harder to remove an electron that is more attracted to the nucleus. And so in this case, choice C is the best choice for those trends properly interpreted. All right, the last question here is asking you to predict a theoretical electron configuration based on a jump in ionization energies. Pause the video, think through this one, take your best guess, and then push play to see how you did. Okay, so here we see there's a large jump between the second and third ionization energies. So what do you think that means? It means that you can continue to remove electrons, and we call that, so the first ionization energy, you've just removed one. The second ionization energy is when you've already removed one and you're trying to move a second one. And the third ionization energy is you're trying to remove a third electron. So ionization energies should go up as you try to remove more and more electrons, because when you remove one, you're removing repulsions, and now everything's more attracted, and then you remove another one and everything's more attracted because the repulsions are no longer there. All right, so what would a jump between the second and third ionization energy mean? Well, it means that removing the first one is relatively straightforward. Removing the second one is only slightly more energy, but then it's a lot more energy to remove a third one. So we're looking for an electron configuration that would describe a situation where you could remove 2 electrons, but then the third one would be very difficult to remove. So if we look at choice A, this is an s orbital that has 2 electrons in it. So it would make sense. This corresponds on the periodic table of beryllium and everything below it. So removing 1 electron would give us a +1 ion. Removing 2 electrons would give us a +2 ion. And then if at that point, everything here would have a noble gas configuration once you remove those 2 electrons. And it would be really hard to remove another electron because now you've got a noble gas configuration and those are so stable. So A actually makes a lot of sense. But let's look at the other options as well. B has 3 valence electrons and 1 of them in the p orbital and then 2 more in the s. Removing all 3 of these should give you a noble gas configuration, so it doesn't make a whole lot of sense why there would be a big jump between 2 and 3. C makes a little bit more sense because if you remove the 2 p electrons, then there is a somewhat of a jump in energy to go to an s orbital. However, it's not going to be as big of a jump as going from a noble gas configuration and trying to remove an electron. So this one's still, it makes more sense than B, but it's not as good as A. And D actually doesn't make much more sense either because you have 3 p electrons. You should be able to remove all 3 of those without a big jump. So A here makes the most amount of sense. And it also brings us to the end of our video. So periodic trends, review them, study them, make sure you understand why, because once you understand why, you don't have to memorize the trends. It all has to do with this idea of Coulomb's law, the attractive forces between the nucleus and the electrons, and the repulsive forces of the shielding electrons that are in between, and that effective nuclear charge that the valence electrons are experiencing.